Hello everyone, welcome to the next lecture in the topic analyzing the spectral reflectance curve of commonly occurring earth surface features. In the last lecture we started discussing about the spectral reflectance curve of vegetation. We have covered what factor influences the reflectance curve of vegetation in the visible part of EMR, and we have also started discussing about the NIR portion. So, today we will continue with that particular topic. So, as I told you, it is the leaf's internal structure, that is the orientation of different types of cells and the air gaps that will control the reflectance of leaf in NIR portion. And I also said that leaves has typically very high transmittance and reflectance in the NIR part. And what we can decipher from this is, like, since each type of vegetation has like a different internal structure, like some leaves will have different orientation of cells, different species of vegetation will have different orientation of cells and so on. So, as different types of vegetation will have different internal structure of leaf, then essentially the NIR portion will be influenced by the type of vegetation that is causing the reflectance and may be useful in vegetation classification or species classification. That is one advantage we can remember it. It is some people have like attempted it to classify different vegetation species by looking at NIR reflectance. This is one thing we have to remember. Second thing what we have to remember is, I told you that the energy in the NIR portion that is entering the leaf will undergo multiple reflectances, that is, as it encounters different surface between a cell and air gap, between a cell and water, it will undergo multiple reflectance, which will cause the outcoming reflectance to be more diffuse. That is, I told you that reflectance can be specular or diffuse, and the final net reflected energy that is coming out of the leaf will be more diffuse in nature when compared with the specular, when compared with say visible portion, which can be specular reflection. That is, normally the EMR which is reflected in a diffuse manner will contain more information about the object that reflected it, that is, it has interacted little bit more with the object that from which it got reflected, and it will carry additional information about the particular object. Normally we prefer to have like a diffuse reflectance than specular, because specular will be like what will happen is high amount of energy will be reflected in one particular direction, which may cause like a bright spot in the image, which may not tell us more information about the object of interest. Say like when we look at like still calm water bodies from certain angle, we may get like a bright reflectance, like a sun glint we call. So, such sort of bright reflectance spots may not provide us more information about the object, but the radiance which is coming in from the object normally, or which is reflected in a diffuse manner, will carry some information about the object of interest. So, essentially the energy in the NIR portion will be more diffuse when compared with the energy that is being reflected in the visible portion of EMR. Okay. Coming back to the general reflectance and transmittance characteristics of a leaf, we will just look at this particular figure in the slide. So, here if you can see, this particular portion is like on the left side of the axis we have reflectance, on the right side of the axis, right side y axis, the secondary axis, we have transmittance. So, reflectance increases from 0 to 100 along this direction here, and transmittance increases from 0 to 100 in this particular, in the secondary axis, from top to bottom. So, if you see, essentially the reflectance and transmittance curves are almost like superimposable on each other. Like if the reflectance is low, transmittance is low, if the reflectance is high, transmittance is high, and so on. So, essentially they are like, they have like a very close relationship with each other, that is reflectance and transmittance. And also we know that reflectance plus transmittance plus absorptance is equal to 1, and hence absorptance is equal to 1 minus reflectance plus transmittance. So, this shaded portion in between is the absorptance or the energy that is absorbed. If you look at these particular things, what we can sense is in the visible domain, that is less than 0.7 micrometers, absorptance is pretty high with very low reflectance and transmittance. On the other hand, when we move to the NIR portion, that is from 0.7 to 1.4 micrometers, reflectance is pretty high, somewhat close to like say 50% or something. Transmittance is also pretty high, something around like say 40-45%, and absorptance is quite low. And again the absorptance increase when we move to the SWR portion. Maybe we will study about SWR portion little later, but what I want you to just observe is compare the absorptance between the visible portion and the NIR portion. In visible, absorptance is pretty dominant with very low reflectance and transmittance, whereas in the NIR portion absorptance is very minimal with really high amount of reflectance and transmittance. And as I already told you, this behavior, this high transmittance and high reflectance is essentially to prevent the leaf from undergoing irreparable damage, and hence leaf will absorb very little amount of NIR. So, maybe the visible portion and the NIR portion can give certain information about the amount or the presence of vegetation and its healthiness. Okay. So, a healthy green vegetation, if you just remember the spectral reflectance curve, we could have observed that reflectance is pretty low in the red portion and the reflectance is very high in the NIR portion. So, maybe we will just try to understand how the reflectance will vary in the red and NIR portion for a vegetation starting from its initial stages to its harvest stages. Okay, so, that is given here in this particular scatter plot. Here what we are going to see is, if we plot red reflectance versus NIR reflectance. So, red is there in the x axis, NIR reflectance is there in the y axis. If we can plot the reflectance, we will be able to clearly decipher between a bare soil line and a vegetation line. That is, we will see in the later part of this lecture or in the upcoming lectures that soil has almost like a linearly increasing curve, almost. So, as the wavelength increases, the reflectance of soil will increase. So, essentially red reflectance and NIR reflectance, it will slightly increase like this. Okay, it will be like a linear line. High reflectance in red normally will have high reflectance in NIR and so on. But for vegetation, as vegetation grows to like a bigger level, then reflectance in NIR will be increasing and there will be strong absorption in the red portion, that is low reflectance in red, high reflectance in NIR. That is, we will come to this particular slide or this particular figure, figure B here. So, let us imagine like one particular pixel or one particular land parcel, which is essentially we are starting with like bare soil. Let us say it is like a small agricultural plot, the farmer is going to prepare the plot for agricultural purposes. So, before agriculture, the farmer will prepare the land, he or she will water the land will be like prepared. So, let us say it is, the point is somewhere here, the reflectance, the red and NIR reflectance is somewhere here. This is like corresponding like wet soil. Wet soil will have relatively lower reflectance in all the bands in compared to a dry soil. Okay. So, now the vegetation begins to sprout and begins to grow. When that happens, as vegetation grows, the reflectance in red will go down because of the strong absorption of red because of chlorophyll pigment. On the other hand, reflectance in NIR will increase. So, this particular point may move something like this along this particular curved line, that is decreasing red reflectance, increasing NIR reflectance. So, there will be like a point where the crop would have reached its maximum growth cycle. After that, the plant will be ready for harvest. Once it is when it reached its maximum growth cycle, it may be ready for harvest. The farmer would have harvested it, and then this particular point may land up somewhere here, indicating like a harvested land containing just like a dry soil without any vegetation. So, this is how a particular pixel where vegetation grows will typically behave. So, what is the take home message from this particular slide is, so vegetation has like a characteristic reflectance, and if we combine the red portion and NIR portion, we will be able to study about like the growth of vegetation. So, as vegetation grows, so essentially reflectance in red portion will go down and down because of high absorption of red wavelength by chlorophyll. On the other hand, when vegetation grows, its leaf size will increase, lot of its internal structure of leaf will develop, and hence NIR will be beginning to strongly reflected and transmitted, and hence the reflectance in NIR will increase. So, that is why if we observe the reflectance of like one particular land parcel in a full growth cycle of a crop, we can observe this particular pattern in which the reflectance data moves or aligns itself. Okay. Now, we have seen a general introduction about behavior of leaf in visible and NIR portion. Now, we will take like leaves in different stages of its senescence, that is different stages of its life cycle, and then we will analyze how the spectral reflectance curve look. So, in this particular slide we have 4 different leaves, a green leaf, a yellow leaf, a red leaf and a dark brown leaf. The dark brown leaf is like kind of dead leaf when the sample was collected from below the tree, and these 3, the green, yellow and red leaf, were still alive, present in the tree itself, and this is collected from on the ground at the bottom of the tree. So, this is like a dead leaf. We will start with a healthy green leaf. For a green leaf, what we are observing is a typical low reflectance in the blue portion, low reflectance in red portion which is like pretty low even compared with blue, and a slightly higher reflectance in the green portion. After this, in the NIR portion, reflectance increases drastically and it remains high almost up to like, say here we are talking about 1 micrometer. Okay. Now, we will move to the yellow leaf. Yellow leaf means there is a change in pigment from chlorophyll. Now, chlorophyll has become like less dominant and some other pigments starts to dominate the leaf's characteristics. So, for yellow leaf what happens is the reflectance in red also increases, reflectance in green also is pretty high and reflectance is low only in blue. So, green plus red combined together will give a yellowish color to the leaf, and in NIR portion still we are observing like quite high reflectance value. Now comes the red leaf. So, after this is like another stage of maturity in leaf. So, there the leaf is strongly absorbing in both blue and green portions, that is chlorophyll is like almost absent and only some other pigments are present. So, this leaf is like almost towards the end of its life cycle. So, what happens, only red reflectance dominates a lot and NIR reflectance slightly reduces. For this brown leaf, in the entire visible portion reflectance is pretty low and then the reflectance in NIR has fallen down. So, the general observation from these 4 leaves are, if the leaf is healthy, then typically the reflectance in red will be very low and leaf will be green in color because of increased reflectance in green portion by chlorophyll. As the leaf moves to its different stages, chlorophyll pigment will begin to reduce, some other pigments may start to dominate, which will give a different color to the leaf, or if the leaf undergoes stress, some sort of stress, water stress, nutrient stress, infestation by some insects, whatever, some other pigments may dominate and hence the color of leaf may change. Essentially it is indicated by change in reflectance in the red portion first. For a healthy leaf, reflectance in red will be very low, but when leaves undergo certain amount of stress or when some other pigment dominates, reflectance in red will increase. If you look at the NIR portion, till the leaf is like almost at its final stages, like for the except for the red leaf, the NIR reflectance was pretty high, because until the leaf's internal structure is damaged completely, leaves will maintain its high reflectance in NIR portion. Only when the leaves internal structure itself is damaged because of like the final stages of leaf, or the leaf is like about to die and fall off, then only NIR reflectance will go down. So, what it means is NIR reflectance will be relatively higher even when the leaf is undergoing significant amount of stress or some other pigment is dominating. Like normally we would have seen in our daily life that when vegetation undergoes water stress, when we do not water our plants, after few days its leaf color will start turning yellow and then the leaf may die, right, we have observed that. So, when the leaf turns yellow, what it means, because of absence of water, the plant underwent or undergoing a water stress, its chlorophyll content is beginning to reduce, it is not able to sustain itself. Some other pigments is now becoming dominant, which gives leaves its characteristic yellowish color or reddish color. That means reflectance in red has already increased, but till then NIR reflectance will be fairly high. Only when the leaf has undergone change in its internal structure itself, like the leaf is now dead, it is now crumbling, then only the reflectance in NIR will be coming down. So, if you look at the visible and NIR portion of the spectrum, only in these two parts, the first signal of leaf senescence or the first signal of leaf stress, whatever, either due to senescence or due to stress, it will be shown characteristically as increased reflectance in red portion rather than decreased reflectance in NIR band. So, you should remember this. I am talking only about visible and NIR range. Whenever leaves is undergoing different stages of its life cycle, or whenever leaves is undergoing some sort of stress, it will be signaled through increased reflectance in the red portion first, then there will be like change in reflectance along the different portion of visible, like reflectance in green may come down, reflectance in red may increase lot in compared to green and so on, and finally only when the leaf internal structure itself is going to change, NIR reflectance will come down. So, visible portion, if you compare visible and NIR, visible is like pretty useful for understanding vegetation stress or vegetation senescence and so on. So, that is why normally we will see in later part of this particular topic of upcoming lectures that combining NIR and red portion or reflectance, combining reflectance in NIR and red portion will help us to understand the healthiness or how the vigor of vegetation that is present in the land surface. Okay, till now we have seen the spectral reflectance property of vegetation in the NIR and visible portions. Now we will move on to understanding the spectral reflectance property of leaf in the SWIR portion, that is wavelength starting from 1.4 to say 2.5 or even 3 micrometers. So, the reflectance in SWIR portion is strongly influenced by leaves water content. As leaves water content increases, reflectance decreases in the SWIR portion. In this particular figure given in the left side of the slide, we have plotted leaves with different water content level and how its spectral reflectance will look. Maybe we will start with leaf with 100% water content, where all the air gaps are filled with water, all air gaps filled with water. We call this the amount of water content in leaf as turgidity. So, turgidity normally refers to the amount of water content within the leaf, it is a general term we use, and if a leaf is completely filled with water, with 100% water, we call that particular leaf as turgid. It is fully turgid, that is it is filled with water. So, maybe we will start with such a fully turgid vegetation, that is like the dark black curve given here. This is a typical characteristic healthy vegetation curve that we have already seen with like very low reflectance in red, very high reflectance in NIR, and if we come to the SWIR portion, the reflectance is relatively lower, that is lower than NIR, but fairly higher than the visible part. And also if you look only in the SWIR portion, that is the 1.4, after 1.4 we can see as wavelength increases, reflectance goes down linearly. So, this we have to remember. In the SWIR part, as wavelength increases, reflectance goes down almost linearly, this we have to remember, and also reflectance in general goes down with increasing water content. Okay. So, this is for like for healthy leaf, this will be the curve, and also there will be like 3 strong dips, like here it is not that it stops at 2.5, but there are like 3 strong water absorption bands in the 1.4, 1.9 and 2.7 micrometer portions of EMR spectrum. That is, as vegetation's water content increases, this particular absorption bands in this 1.4 and 1.9 will become very dominant and it will become very strong. And as the leaf's water content decreases, say now the leaf content is water content moved to 75%, reflectance has increased slightly and also the absorption band has become slightly less stronger. And as we move higher and higher, we can see that, say we will just go to this 5% curve, this dotted line, the top line, reflectance is very high in the SWIR portion, and the characteristic dips seen around this 1.4 and 1.9 micrometers are almost absent, that is the dips are like present only like very minimally. And you can also see that even at this stage of very low water content, NIR reflectance is pretty high, actually like it will also increase with increasing in with the drying out of leaf, but you can see that at 5% means vegetation will undergo like a significant water stress, it will not be able to do photosynthesis with full efficiency, and hence red reflectance is increased, also green reflectance is increased, that this leaf is not yet died, not yet undergone like full effect of water stress, only like water has reduced at that particular time, and hence it shows very high reflectance. So, what essentially it means is the amount of water content will in general influence all portion, like as the water content increases the reflectance will go down, but this is very strongly seen in SWIR portion of vegetation. So, if we want to study vegetation water stress, the immediate signal will be coming from SWIR portion, like it may take some time for vegetation to undergo stress for the change in red reflectance. It may take still longer time for the vegetation to for the leaves internal structure to completely get disturbed for a reduction in NIR reflectance. But in SWIR portion, as soon as the vegetation water content changes, the reflectance will change. So, this is one of like the most suitable band for understanding or for studying about how much water content a leaf has. So, as the leaf's water content increases, the reflectance will go down pretty fast in the SWIR portion of electromagnetic spectrum. But if we want to use these characteristic dips 1.4 and 1.9, we will not be in a position to use them, because we have already seen that atmospheric absorption also plays a major role in remote sensing, and the same portions 1.4, 1.9, 2.7 are water vapor absorption band that is present in atmosphere. So, when we take a remote sensing image, we will not be able to clearly see these particular dips. We will not be able to understand whether these dips are due to atmospheric water vapor or due to vegetation water content. So, we will not be using this, but the other portions, other surrounding portions, say roughly 1.5 to 1.7 or after 2 All these things will carry certain information about leaf water content, which we will use it for studying whether the leaf is having water or not. So, this particular slide gives another example of how like a green grass and a dry grass look. It is like a green grass with good amount of water and a dry grass which is like almost dead at its dead stage. You can see like as the leaves became dry, the reflectance increases in general in almost all bands, and this is like undergone lot of stress, and hence the reflectance in visible portion also has changed drastically. So, very high reflectance in red portion, green portion and everywhere, but NIR still remains. So, NIR is not a very good portion to study the water stress, but it helps us to study some other thing we will see later. But for understanding water stress, it is always good to use the SWR portion, which will first show immediate signals. It will take some lag time or some time will be used up before water stress influences leaves pigment and causes a change in leaf color. It will take some time and it will take further time to change the reflectance in NIR. So, as leaf dries out, its reflectance will increase. This is what we have to remember. So, I already told you that the 1.4, 1.9 or the 2.7 micrometer wavelength, which are characteristic water absorption bands, we will not be in a position to use it for remote sensing purposes because of atmospheric absorption. So, when Landsat thematic mapper, one of like the early sensors, Landsat 5 satellite was launched, its one of the major application was global vegetation monitoring. So, the bands were chosen such that different properties of vegetation are observed clearly. That is, it had bands in say green band and red band, where it absorbs the pigments contained within the leaf. Then it also had a NIR portion, like it had a band in this particular NIR portion, which will help us to tell whether the leaf is really healthy or not, which signals about leaf's internal structure. Then it also had a band around like 1.5 to 1.7 micrometer range, which will help us to study the leaves water content. So, different bands of this particular sensor was chosen such that different properties of leaves or different properties of vegetation can be properly observed and understood. So, essentially in this particular lecture what we have seen is how reflectance of vegetation will vary in the NIR and SWR portion. So, primarily in the SWR portion, it is the leaves water content that controls the spectral reflectance property of leaf. So, just as a summary of the entire thing, the spectral reflectance curve of vegetation can be divided into 3 portions: the visible part, NIR part and SWR part. In the visible part, the leaves pigments or the absorption by those pigments will dominate the spectral reflectance pattern. In the NIR portion, the leaves internal structure will dominate the spectral reflectance pattern, and then in the SWR portion, the leaves water content will influence the spectral reflectance property. So, whenever vegetation undergoes water stress, it will be first signaled in the SWR portion, and when the vegetation undergoes some sort of stress because of lack of water for some time or change in growth cycle, there will be like a change in reflectance in the visible portion because of change in pigments. And pretty late, like once the vegetation undergoes a significant amount of stress for a prolonged time, then only reflectance in NIR will change. Till then reflectance in NIR will be pretty high. So, with this we will end this particular lecture. Thank you very much.